Okay, we started late today. Hello. So let's jump straight into it. Just want ChatGPT to explain this code. We wrote it a couple weeks ago. This is the one that does the finger recognition on this side. So this guy, you have the green. Oops, it just stopped working. Yep, just crashed on me, didn't it? Just copied the code and it crashed. It's not cool. Something with the camera, I guess. It has to explain, but then it's making modifications. Initializing video capture. Yeah, that's right. Display the frame. Yeah, that's the holistic hand detection thing. That's right. Just checking my live stream on Google because that's the only way to get a link for it. Putting it on, so many using Twitter. Well, I'm not really using it. I'm just posting on it and then running away. I don't like Twitter. It's really bad. Figure out why this code stopped working. I suspect it happened before when the camera started playing up. Camera just being. Actually takes some time to start streaming and everything. Make sure I'm using the right microphone and sharing the link because I'm not logged in. Oops. In the same place. So it's sometimes hard to do. Can talk to it live. He said ChatGPT is out. ChatGPT 5 is me. No, that's not a false advertisement. And you can talk to it live. What else were we trying to do? This code. read this quickly.
The given code is an example of how to use the media pipe library with OpenCV to perform holistic body pose estimation and hand tracking in real time from a video feed. Let's break down the code step by step. Import necessary libraries. The CV2 module is from OpenCV, which is used for image processing and video capture. The media pipe library provides various pre-built solutions for different computer vision tasks, including holistic and hand tracking. Initialize media pipe holistic model and hand tracking. Python. Here, we create instances of the media pipe holistic and hand tracking models using their respective classes. Initialize video capture. This line initializes the video capture object using the default camera, 0. In the loop, we continuously read frames from the video capture object. The captured frame is in BGR format, but media pipe requires RGB input. So, we convert the frame to RGB format. Process the frame with media pipe holistic model. Captured frame is in BGR format, but media pipe. We process the RGB frame using the media pipe holistic model, which provides various outputs like face landmarks, pose landmarks, and left/right hand landmarks. We process the RGB frame using the media pipe hand tracking model, which provides outputs like multi-hand landmarks and handedness, whether the hand is left.
Right, so we had this error message that is coming up with. Trying to fix this quickly. Something with the vision. I don't know. It could be that this GPT is providing outdated code.
The error message you provided indicates that an assertion failed in a CVT color function from the OpenCV library. The specific assertion that failed is _src.empty, which means that the input image _src is empty. This error can occur if there is a problem with reading frames from the video capture or if the video capture is not initialized properly. Here are a few possible reasons and solutions. Verify that your camera is connected and working correctly. Make sure it is not being used by any other application. Check if the cap.read function is returning frames successfully. You can add a print statement to check the ret variable. If ret is false, it means that no frame was read. This could be due to an issue with the camera or video capture. Ensure that your camera has the correct index. The line cap equals CV2.videoCapture, 0, initializes the video capture object with index 0, which refers to the default camera. If you have multiple cameras or if the default camera is not working, you can try changing the index to a different value, example 1, 2, etc. To the camera, you may need to use a different video source. For example, you can try reading a video file instead of a live camera feed.
As the camera is connected and everything. Why is it creating?
Make sure to check the above points and ensure that the video capture is functioning correctly. If the issue persists, please provide more information about your environment and how you are running the code so we can assist you further.
Yeah, it must be the camera just reconnected. Reconnecting the camera. Okay, so you can see my hands. Yeah, the yellow ones has a number, so those are they're like in white. I don't know if you can see it, but there are numbers on each point. So that's handy, and that's what we have in this data set as well. For spelling with sign language, which we're meant to recognize. Just yes, it's creating TensorFlow Lite, which is also the condition for the competition. But I don't know why am I using TensorFlow Lite.
The message info, created TensorFlow Lite's impact delegate for CPU, is an informational message that indicates the successful creation of a TensorFlow Lite's impact delegate for CPU execution. When using TensorFlow Lite for running models on CPU, delegates can be employed to optimize the performance. The Zimpact delegate is one such delegate provided by TensorFlow Lite. It leverages the Zimpact library, which is a highly optimized deep learning inference library for CPUs. By creating the Zinpack delegate, TensorFlow Lite is indicating that it will use the Zinpack library to accelerate the execution of the model on the CPU, resulting in improved inference speed and efficiency. This message is usually displayed as part of the initialization process when TensorFlow Lite is configuring the environment for model execution. It serves as an indication that the Zinpack delegate has been successfully set up and is ready to be used for inference. Overall, this message is informative and confirms that TensorFlow Lite is utilizing the Zinpack delegate for optimized CPU execution of the models.
Yeah, still, it's not this code, but the other code is actually training the model. Where is it? Yeah, this one. So that's the American Sign Language competition. We have these bits installed. We're running it in Jupyter Notebook. It's currently doesn't have anything. Might as well just run all. Last week we had some error message there, so we need to fix it. Hopefully GPT can do it for us. So the code is running, seems to be running on a CPU. Yeah, it's not using GPU at all. It's a problem. So I need to check where is it at now, because if it's training, I trained the model already, but then I had trouble loading it. So I can try loading again, but I think it started training already. Just go to, yeah, so go to is a good button. Go to the running cell. And yeah, it's retraining that model again. Which I'm pretty sure we did before. Also, I was trying to make it run on a GPU, but couldn't really do it. But this code here, that's the one that's running stuff from the camera, is also running a CPU. And I don't know why. This in the back. What is this thing anyway? Yeah, it's a TensorFlow library, sort of optimization for CPUs, but
Zinpack is a library developed by TensorFlow Lite that provides highly optimized implementations of deep learning operations for efficient inference on CPUs. It stands for Zinpack Neural Network Library and is designed to accelerate the execution of neural networks on CPUs, especially in resource-constrained environments. Zinpack offers optimized implementations of various common operations found in deep learning models, such as convolutions, pooling, matrix multiplication, activation functions, and more. These implementations are carefully tuned to take advantage of CPU architectures, making use of vectorization, parallelization, and other optimization techniques to achieve faster and more efficient execution. By utilizing Zinpack, TensorFlow Lite can significantly improve the performance of deep learning models on CPU devices, allowing for faster inference times and reduced resource utilization. This is particularly beneficial for mobile and edge devices that may not have access to dedicated hardware accelerators like GPUs. Overall, Zinpack is an integral part of TensorFlow Lite's strategy to enable efficient and portable deep learning inference across a wide range of devices, making it a valuable tool for developers working with CPU-based deployments of deep learning models.
yeah, I'll just use that for now. Just hoping my stream is still okay. You see I'm not dropping any frames in OBS, so that's good. Sorry, jumping between two codes. Yeah, this is pre-recorded data, so this is essentially coordinates of hands of someone spelling out phrases using sign language. Yeah, we have couldn't find my GPU, even though I have one. I'm actually using it at the moment, so it's installed correctly and everything, but TensorFlow, for whatever reason, could not find it, which is a bit frustrating. And now we're training a model again. So currently the loss function is 0.8. Oh, it's dropping down to 0.7. We did it once before. We actually haven't changed much. So we expect it to go all the way to 0.5 or so. Just open previous notes. Remove um, right. So this is what the training will do eventually. Oop. So it's 12 epochs. Could probably reduce the number of epochs. And I was trying to figure out if it's deciding how many epochs to do. Is it hardwired? Not hardwired, it's not electronics, but you know what I mean. If it's preset in the code, or it's deciding based on performance when to stop. Because the validation loss function starts doing this bump back up, so maybe that's why it stops. And this one is doing a 1080 2080 split for training and validation. So I don't know if changing that will make any difference or not. It's actually should, because in theory, if the training loss function keeps going down, still going down quite drastically. So we're now only at the epoch 3. Takes forever. Really need to engage. Let's stop this for a sec. Really need to engage a GPU. Well, first, even on CPU, I don't know why it's going to using all 100%. If we just have a look how to limit CPU usage.
To limit CPU usage when running a program, you can use techniques such as setting process affinity or adjusting the CPU priority. However, please note that the exact methods and options available may vary depending on your operating system. Here are a few general approaches you can try. Set CPU affinity. CPU affinity allows you to specify which CPU cores or processors
And edit on Windows 11. I don't know if 11 makes any difference. Shouldn't make any difference in theory, but just put it there.
On Windows 11, you can limit CPU usage for specific processes using the built-in Task Manager utility. Follow these steps to set CPU usage limits. Open Task Manager. Right-click on the taskbar and select Task Manager from the context menu. Alternatively, you can press Ctrl plus Shift plus Escape on your keyboard to open Task Manager directly. Switch to the Processes or Details tab. Depending on your Task Manager view, either click on the Processes or Details tab to see the list of running processes.
I want to automate this in Python. and TensorFlow says there's none.
In TensorFlow, there is no direct built-in functionality to limit CPU usage on Windows 11. However, you can achieve similar results by configuring the TensorFlow session with CPU-specific options and by setting the CPU affinity of the Python process. Here's how you can do it. Set the number of CPU threads. By default, TensorFlow will utilize all available CPU threads. You can limit the number of threads by setting the omp_num_threads environment variable before importing TensorFlow. For example, Python. Set interop and interop parallelism. TensorFlow uses interop and interop parallelism to control how operations are distributed across CPU threads. You can configure these options to control CPU usage. For example,
So let's try this. Hit open resource monitor for this. Yeah, let's limit the, just put it away for a sec. So we stop this one. Can do this again. Get rid of that. So do I need to do just one of those or copy this as the prompt?
by default, TensorFlow will utilize all available CPU threads. You can limit the number of threads by setting the omp_num_threads environment variable before importing TensorFlow. For example, set interop and interop parallelism. TensorFlow uses interop and interop parallelism.
Yeah, let's just try it out. It's still still using 100%. What? It didn't work, did it? And what happens if you import again? Wait, am I even using TensorFlow? Model. Yeah, Keras losses the categorical cross entropy.
TensorFlow uses interop and interop parallelism to control how operations are distributed across CPU threads. You can configure these options to control CPU usage. For example, you can use the SUDL library to set the CPU affinity of the Python process, restricting it to specific CPU cores. Here's a By limiting the number of CPU threads, setting interop and interop parallelism, and specifying CPU affinity, you can control the CPU usage of TensorFlow on Windows 11. Adjust these settings according to your requirements and available hardware resources. Note that limiting CPU usage may impact the performance of your TensorFlow models. It is recommended to monitor the model's execution time and resource usage to find the optimal balance between CPU utilization and performance for your specific use case.
Right, so it sounds that I need to do these other steps as well. Oops. Try it again. We should be only using 4 cores. Get an error. But I'm not running it.
Apologize for the incorrect information provided earlier. You are correct that TensorFlow throws a runtime error when attempting to modify interop parallelism after initialization. In TensorFlow, the interop parallelism setting is initialized once at the beginning and cannot be modified during runtime. However, you can control the interop parallelism to limit CPU usage. Here's an updated approach. By setting intra_op_parallelism_ threads in a config proto object, you can limit the number of threads used by TensorFlow within each operation. This allows you to control CPU usage to some extent. Adjust the number_threads variable according to your requirements. Note that the above code uses the tf.compat.v1 module, as tf.config_proto is part of the TensorFlow 1.x API. If you are using TensorFlow 2.x, you can still use the compatibility module to access the TensorFlow 1.x API. Please note that restricting the CPU usage may impact the performance of your TensorFlow models.
Yeah, that's fine. I don't get it. I gave you this code that said there's a mistake and gave you a totally different code. Number of threads 4. Okay. It's actually running. Oh, and CPU is still at 100%. Why? Doesn't look like it. Doesn't look like it using only 4 cores, does it? So it doesn't work. %, CPU. There's something about the, because I have this sentence already before, and there's something about Python. No, that was commented out now. It needs to be done mostly before the first import. So what if you import a module twice? Yeah, it will understand my spelling mistakes because it's smart enough.
Importing a module twice in Python does not generally cause any issues. The Python interpreter has built-in mechanisms to prevent duplicate imports and ensures that a module is imported only once, regardless of how many times it is called. When a module is imported for the first time, its contents are executed, and the module is added to the sys.modules dictionary. On subsequent import statements, Python checks if the module already exists in sys.modules and, if so, it references the already imported module rather than executing the contents again. Here's an example to demonstrate this behavior. When you run main.py, the output will be Mathematica. Copy code. Module example imported. Module imported multiple times. As you can see, the module is only imported once, despite calling the import statement multiple times in the main.py file. However, it's important to note that if a module contains code that has side effects, example, modifying global variables or executing functions, those side effects may occur multiple times if the module is imported multiple times. Therefore, it's generally recommended to import a module only once to ensure consistent behavior and avoid any unintended side effects. In summary, importing a module twice in Python does not cause any issues, and the interpreter handles it efficiently by importing the module only once.
Yeah, but it didn't apply the using less cores. Terminal. Right, that's all the variables. I might just try it the next time. Currently, we're still on the third epoch. Okay, let's stop this again, and we'll make a couple of changes this time. Okay, don't need that line. We want to take all this. Let me just check this model H5. Yeah, it actually exists. It's been modified last week. And we changed the name, so it can actually find it. Oh, this will be messy. Should have just trained the model once and then created a new model. I actually tried doing it last time. It didn't work so well. Right, so when we're importing a TensorFlow, break it here, and again. Oops. What is this here? So this is TensorFlow limit usage on Windows 11. That's for our prompt. We don't need that anyhow. Comment this out because we have it in here. Right, make just another change. We want to, no, let's run all, oops. get the images created using media pipe. That's the images that we have. Someone signing. This one is training the model. We're still using 100% CPU. But that didn't work, did it?
If you are still experiencing 100% CPU usage despite setting the number of CPU threads and intra-op parallelism, there could be other factors causing high CPU utilization. Here are a few additional suggestions to investigate and potentially address the issue. Check for other processes or applications. Ensure that there are no other resource-intensive processes or applications running on your system that might be consuming significant CPU resources concurrently. Verify TensorFlow version. Make sure you are using the latest version of TensorFlow. Newer versions often include performance optimizations and bug fixes that can improve CPU utilization. Enable TensorFlow GPU support. If your system has a compatible GPU, consider enabling TensorFlow GPU support. GPU acceleration can offload computation from the CPU, reducing its overall usage. Refer to the TensorFlow documentation for information on installing and configuring GPU support. Update GPU drivers. If you are using GPU acceleration, ensure that your GPU drivers are up to date. Outdated drivers can cause compatibility issues and impact performance. Optimize your TensorFlow code. Review your TensorFlow code for potential inefficiencies. Enable TensorFlow GPU support. If your system has a compatible GPU, consider enabling TensorFlow GPU support. GPU acceleration can offload computation from the CPU, reducing its overall usage. Refer to the TensorFlow documentation for information on installing and configuring GPU support. Update GPU drivers. If you are using GPU acceleration, ensure that your GPU drivers are up to date. Outdated drivers can cause compatibility issues and impact performance. Optimize your TensorFlow code. Review your TensorFlow code for potential inefficiencies. Consider optimizing data loading, batching, and model architecture to improve performance and reduce CPU usage. Monitor memory usage. High memory usage can indirectly lead to increased CPU usage. Ensure that your system has sufficient memory available and monitor memory usage while running TensorFlow to identify any potential memory-related issues. Consider hardware limitations. In some cases, high CPU usage may be due to hardware limitations. If your system has a low-performance CPU or limited cores, it may struggle to handle complex deep learning models efficiently. Upgrading your hardware could provide better performance. It's important to note that deep learning models can be computationally intensive, and achieving low CPU usage without sacrificing performance may not always be feasible. However, by investigating these factors and making appropriate adjustments, you can optimize your setup and minimize unnecessary CPU usage.
Yeah, the other thing is can't seem to solve the limiting the CPU usage. Or last week I was trying to transfer processing onto the GPU without much success. But the third thing, sorry, there's too many things, but bear with me. The third thing is that we're currently doing a 1080 split, but considering the training loss function keeps reducing, might just try a different ratio for it. So let's find that code. Let's stop this for a sec. Let's find the split. It's an 80. What's another recommended split percent?
The resulting value of train_len represents the number of examples or records that will be used for training, considering an 80/20th split with the TF_records dataset. This approach is often used to divide a dataset into a training set and a validation, or testing, set, where the training set contains the specified percentage, 80% in this case, of the total dataset, and the validation set contains the remaining percentage, 20% in this case.
So is 80/20 split a standard thing to do?
The 80/20th split, also known as the Pareto principle or the 80/20th rule, is a commonly used split for dividing a dataset into a training set and a validation, or testing, set. However, it is not necessarily a standard or fixed rule that applies in all situations. The choice of the split ratio depends on various factors and considerations specific to the problem and the available data. Here are a few points to keep in mind. Data availability. The size of your dataset plays a role in determining the split ratio. If you have a large dataset, you may have more flexibility in choosing the split ratio. However, if you have a smaller dataset, you might want to allocate a larger portion for training to ensure sufficient data for model learning. Task complexity. The complexity of the task you are working on can influence the split ratio. For simpler tasks, a smaller validation set might be sufficient. But for more complex tasks or models that require careful tuning, a larger validation set can provide a more reliable estimate of performance and help prevent overfitting. Overfitting concerns. Overfitting occurs when a model learns to perform well on the training data. The size of your dataset plays a role in determining the split ratio. If you have a large dataset, you may have more flexibility in choosing the split ratio. However, if you have a smaller dataset, you might want to allocate a larger portion for training to ensure sufficient data for model learning. Task complexity. The complexity of the task you are working on can influence the split ratio. For simpler tasks, a smaller validation set might be sufficient. But for more complex tasks or models that require careful tuning, a larger validation set can provide a more reliable estimate of performance and help prevent overfitting. Overfitting concerns. Overfitting occurs when a model learns to perform well on the training data but fails to generalize to unseen data. To mitigate overfitting, having a larger validation set can help in evaluating the model's performance on unseen data and detect potential overfitting issues. Cross-validation. In some cases, instead of a single 80/20th split, cross-validation techniques such as k-fold cross-validation or stratified sampling may be employed. These approaches involve dividing the dataset into multiple subsets and performing training and evaluation across different combinations, providing a more comprehensive assessment of model performance. Domain-specific considerations. Different domains and specific problem requirements may warrant different split ratios. For example, in certain cases where data is scarce, a higher ratio, example, 90/10, might be used to allocate more data for training. Alternatively, in scenarios where a large validation set is desired for rigorous evaluation, a lower ratio, example, 70/30, might be chosen. Ultimately, the choice of the split ratio should be based on careful consideration of the factors mentioned above, as well as any domain-specific requirements and constraints. It is a best practice to experiment with different split ratios and evaluate the impact on model performance to determine the most suitable ratio for your specific problem. Regenerate response.
And the number of epochs is a 13. But searching where? Let's try just to save time. Actually, probably need more epochs. Then in each now we need to make it longer. Just run quickly and see how we can improve the speed of it. It's reducing very slowly. The problem that during streaming I'm using the GPU, so that would not moving to GPU. Now I want to know how to do it so I can train like overnight and stuff, but if it takes this long, also this optimizer is not great. What mainly determines the speed of training?
The speed of training in machine learning models is influenced by several factors. Here are some of the key determinants. Dataset size. The size of the training dataset plays a significant role in training speed. Generally, larger datasets require more time to process. Training on a small dataset may be faster since there are fewer examples to process during each iteration.
So what's the size? I don't know what be like tokens or something, but generally train landmarks is 95 gigabyte. Yeah, those are the Parquet files. And then you have the pre-processed stuff, the TF TensorFlow record files, which is only 5.4 gigabytes. What happened to all the data?
Model complexity. The complexity of the machine learning model affects training speed. Models with a larger number of parameters and more complex architectures typically require more time to train. Deep neural networks with multiple layers and a high number of neurons per layer tend to be more computationally expensive to train compared to simpler models like linear regression or decision trees. Hardware resources. The hardware used for training, particularly the processing units, CPUs or GPUs, can have a significant impact on training speed. GPUs, with their parallel processing capabilities, are commonly used to accelerate training for deep learning models. The availability of multiple GPUs or specialized hardware accelerators like TPUs, tensor processing units, can further enhance training speed. Optimization techniques. Various optimization techniques can help speed up training. Techniques like mini-batch gradient descent and stochastic gradient descent, SGD, process subsets of the training data in each iteration, reducing the computational load. Additionally, using efficient optimization algorithms, such as ADAM or RMSprop, can improve training speed by converging faster.
So I'm using the Adam. Well, not me, this code. I should have the Adam somewhere in the code. Here's optimizers. And this number seems way too small. Is it only me?
The line of code you provided initializes an ADAM optimizer in Keras with a learning rate of 0.0001. Here's a breakdown of how it works. Keras.optimizers ADAM. This part imports the ADAM optimizer from the Keras library. ADAM is a popular optimization algorithm commonly used for training deep learning models. It combines the benefits of both AdaGrad and RMSprop to achieve efficient and adaptive learning rate optimization. 0.0001 This specifies the learning rate parameter for the ADAM optimizer. The learning rate determines the step size at each iteration of the optimization process. A smaller learning rate can result in slower but more precise convergence, while a larger learning rate can lead to faster convergence but with the risk of overshooting the optimal solution. A smaller learning rate can result in slower but more precise convergence, while a larger learning rate can lead to faster convergence but with the risk of overshooting the optimal solution. By setting the learning rate to 0.0001, you are configuring the ADAM optimizer. Risk of overshooting the optimal solution. By setting the learning rate to 0.0001, you are configuring the ADAM optimizer to use a relatively small learning rate, which can be beneficial in cases where you want to make smaller updates to the model weights at each iteration. Here's an example of how you can use this ADAM optimizer in a Keras model training loop. This example, the ADAM optimizer with a learning rate of 0.0001 is passed as the optimizer argument in the compile function. This configures the model to use the ADAM optimizer during training with the specified learning rate.
I want to expand on this one. Why is it apologizing?
In practice, the choice of a learning rate depends on the specific problem, model architecture, and dataset. The value 0.0001 for the learning rate is not necessarily considered a small learning rate. It is a commonly used learning rate value that falls within a typical range for many deep learning tasks. However, the appropriateness of this learning rate depends on the specifics of your problem and dataset. The optimal learning rate for training a neural network can vary significantly depending on factors such as the model's complexity, the data scale, and the optimization algorithm being used. In practice, it is recommended to experiment with different learning rates to find the value that leads to the best convergence and performance for your specific task. If you find that the model is not converging or training too slowly with a learning rate of 0.0001, you can try adjusting the learning rate by increasing or decreasing it. Common strategies for finding a suitable learning rate include learning rate schedules, learning rate decay, or using adaptive learning rate algorithms such as cyclical learning rates, CLR, or learning rate range. Common strategies for finding a suitable learning rate include learning rate schedules, learning rate decay, or using adaptive learning rate algorithms such as cyclical learning rates, CLR, or learning rate range test, LRRT. It's important to note that the choice of learning rate is problem dependent, and finding an optimal learning rate often requires experimentation and fine-tuning.
Yeah, there's a lot of trial and error in these things. I want to actually understand. Apparently, can do a learning rate test. Was it apologizing again? I just wanted to expand on one of the items it mentioned.
I apologize for the confusion caused by the incorrect acronym mentioned in the previous response. The correct term is learning rate range test, LRRT, not learning rate range finder. The learning rate range test, LRRT, is a technique used to determine a suitable learning rate range for training deep learning models. The learning rate range test.
Yeah, it did use learning rate range test, LRRT, and then it's apologizing, saying confusion caused by incorrect algorithm mentioned previous response. The correct term is test, not learning finder, but it never used the finder, did it? Did it ever use finder? I'm just curious. No. Yeah, a bit of a hallucination there in live hallucination. The other thing I don't understand is people swear by ChatGPT 4. I'm sure 5 is on the way, 6, 7, 8. How do you know it's any better? I mean, it's the same system. Yes, more tokens. But yeah, wondering if anyone actually compared the two side by side. It's probably be almost impossible thing to do.
The learning rate range test, LRRT, is a technique used to determine a suitable learning rate range for training deep learning models. It helps in selecting an initial learning rate that allows the model to converge effectively and quickly. The LRRT involves gradually increasing the learning rate during the initial phase of training while monitoring the loss or a chosen performance metric. The learning rate is increment over a predefined range, typically on a logarithmic scale. The LRRT follows these general steps. Define an initial learning rate range. Start with a small learning rate value, example, 1 times 10 to the power of negative 6.
Yeah, it essentially just tells you to guess what it should be. Anyway, I don't know if this number is standard or not. This was in the original example. It seemed to be too small. That's also pretty sure what's causing the training, the fitting of the model to take forever. Just 1 out of 15 epochs, and it will take that many milliseconds per epoch. Not sure. And we did change the split from 80-20 to 50-50. Guessing that if the training loss keeps going further down, then not sure what is the reason for the validation set loss function to have a very different shape. See if you do it like 50-50. It should be properly randomized as well. Then you would expect them to both go down. There should be no major difference between the two sets.
Define an initial learning rate range. Start with a small learning rate value, example, 1 times 10 to the power of negative 6, and a larger learning rate value, example, 1. These values should encapsulate a broad range of potential learning rates. Train the model, gradually increase the learning rate over the defined range while monitoring the loss or performance metric. It is common to use a few training iterations, batches, for each learning rate value. Plot the learning rate versus loss or performance metric. Create a plot of the learning rate on the x-axis and the corresponding loss or performance metric on the y-axis. Analyze the plot, look for specific patterns in the plot. Typically, you will observe a period where the loss decreases and then starts to increase again. This is known as the learning rate sweet spot. Choose the learning rate at the steepest point of the loss decrease as the initial learning rate for further training. By using the LRRT, you can avoid setting an arbitrary learning rate and instead determine an initial learning rate that promotes efficient convergence. It allows you to identify a learning rate range that is neither too high, leading to divergence, nor too low, leading to slow convergence. Several libraries and frameworks, such as FastTie and PyTorch Lightning, provide built-in functions or utilities to perform the LRRT automatically. These tools handle the training loop and learning rate scheduling, making the process more straightforward. Keep in mind that the LRRT is not a one-time process. It is recommended to periodically perform LRRT during model development or when adjusting other training parameters to account for changes in the model or data characteristics. Regenerate response. Free research preview. ChatGPT may produce inaccurate.
When it's mentioning PyTorch, wondering. Yeah, why did it suddenly jump into talking about PyTorch? No, stop generating this. What I'm wondering about is so this PyTorch Lightning, I wanted TensorFlow equivalent to PyTorch Lightning.
TensorFlow does not have an exact equivalent to PyTorch Lightning, but it provides similar functionalities through different libraries and frameworks. Let's explore some alternatives in TensorFlow that offer similar capabilities to PyTorch Lightning. Keras. Keras is a high-level neural networks API that comes bundled with TensorFlow. It provides a user-friendly interface for building and training deep learning models. Keras simplifies the process of defining models, handling training loops, and monitoring training metrics. It offers a modular and intuitive API, making it easy to prototype and experiment with different model architectures and configurations. TensorBoard. TensorBoard is a visualization toolkit provided by TensorFlow. It allows you to monitor and visualize various aspects of your model's training and evaluation, including metrics, loss curves, histograms, and more. TensorBoard enables efficient tracking of training progress, debugging models, and comparing different experiments. It provides a web-based interface for visualizing and analyzing TensorFlow runs. TF Estimators. TensorFlow Estimators is a high-level API for building and training machine learning models. It offers a consistent interface for various types of models, including linear models, deep neural networks, and boosted trees. TF Estimators handle the training loop, batching, input functions, and model exporting. It provides a convenient abstraction for managing training and evaluation without dealing with low-level details. TF Agents. TF Agents is a library specifically designed for reinforcement learning, RL, in TensorFlow. It offers a high-level interface and tools for developing RL algorithms and training agents. TF Agents provides common RL building blocks, such as agents, networks, environments, and replay buffers. It simplifies the process of defining RL workflows and experimenting with different algorithms. While TensorFlow does not have a direct equivalent to PyTorch Lightning, these libraries and tools within the TensorFlow ecosystem offer similar functionalities and can help streamline the model development process, manage training loops, and monitor training progress.
Is this a standard way of monitoring training progress? Because it's not great, to say the least. And where's this number coming from? What is it, 632? What does it found that 10 times, but would not actually show it. What? Was a number of this setting up the model parameters. Code layer. Right, batch size 64. It's just converting the creating function to convert the data. Convert function. Right, so currently we changed to 0.5 split ratio. It used to be 0.8. Originally 8%. Now we changed to 0.5. It's okay. Actually, the two data sets. These annotations are actually provided by tab 9. Which which is a sort of replacement for Copilot, GitHub Copilot. Just do things step by step. In what is it, a class in Python?
In Python, a class is a blueprint or template that defines the structure and behavior of objects. It serves as a blueprint for creating instances of that class, which are individual objects with their own set of attributes and methods. A class encapsulates data, attributes, and functions, methods, that operate on that data, allowing for the creation of reusable and organized code. Here's an example of a simple class. In this example, the person class has two attributes, name and age, and one method, greet. The underscore underscore init underscore underscore method is a special method called the constructor, which is executed when a new instance of the class is created. It initializes the attributes of the object with the values passed during instantiation. To create an instance of the class, we use the class name followed by parentheses, similar to calling a function. The instance, person1 in this case, can then access the attributes and methods. To create an instance of the class, we use the class name followed by parentheses, similar to calling a function. The instance, person1 in this case, can then access the attributes and methods defined in the class using dot notation, person1.name, person1.greet. Classes provide a way to organize related data and functionality, allowing for code reusability, encapsulation, and abstraction. They are a fundamental concept in object-oriented programming, OOP, and are widely used in Python and many other programming languages.
So there are two classes, token embedding, landmark embedding, token embedding. tokenizing the input. And the second class is embedding layer for tokenizing the input. Why is it the same? There's no. That's not right. So I will explain some random variable from the function. Plain Python. I was writing code if I just asked to explain it.
The code snippet provided defines a class called token embedding, which is a subclass of layer in TensorFlow. Let's break down the code and understand its components. The token embedding class inherits from the layer class in TensorFlow. By inheriting from layer, the token embedding class gains access to various functionalities and attributes provided by the base class. The __init___ method is the constructor of the token embedding class. It is executed when an instance of the class is created. The method takes three arguments, number_vocab, maxlen, and number_hid, which are used to initialize the attributes of the class. Within the __init___ method, the super.__init___ statement is called. This invokes the constructor method, the super.__init___ statement is called. This invokes the constructor of the base class, layer, and initializes it. The token embedding class has two attributes. Self.emb, an instance of the embedding layer from tf.keras.layers. It is used for token embedding and maps the vocabulary tokens to hidden dimensional vectors. The number_vocab specifies the number of vocabulary tokens, and the number_hid specifies the hidden dimension of the embedding outputs. Self.pos_emb, another instance of the embedding layer. This layer is used for positional encoding. It maps the position indices of tokens in a sequence to hidden dimensional vectors. The input_dim is set to maxlen, which represents the maximum sequence length, and the output_dim is set to number_hid. The provided code demonstrates the construction of a custom token embedding layer, which combines token embeddings and positional encodings. By using this layer, you can create more advanced models that incorporate both token information and positional information when processing sequential data. Using this layer, you can create more advanced models that incorporate both token information and positional information when processing sequential data. The code snippet you provided is part of the token embedding class and defines the call method. The call method is an essential method in TensorFlow models and is used to specify the forward pass or inference logic of the layer. Let's understand the code. The call method takes x as an input argument, which represents the input data to be processed by the layer. Maxlen equals tf.shape, x-1, calculates the maximum sequence length, maxlen, based on the shape of x. It extracts the last dimension of x, which represents the length of the sequence. X equals self.emb, x, applies the embedding layer, self.emb, to the input x. It converts the input tokens to their corresponding embedding representations. Applies the embedding layer, self.emb, to the input x. It converts the input tokens to their corresponding embedding representations. Positions equals tf.range, start equals 0, limit equals maxlen, delta equals 1, creates a tensor positions that represents the relative positions of the tokens in a sequence. It generates a sequence of numbers from 0 to maxlen, 1, where delta equals 1 represents the step size. Positions equals self.pos_emb, positions, applies the positional embedding layer, self.pos_emb, to the positions tensor. This maps the relative positions to their corresponding embedding vectors. Finally, return x plus positions adds the positional embeddings to the original token embeddings, x. The positional embeddings capture the positional information of tokens in the sequence, enhancing the representation learned by the token embeddings. Overall, the call method combines the token embeddings, x, and positional embeddings, positions, to produce the final output of the token embedding layer. The combined embeddings capture both the token and positional information, which can be further processed by subsequent layers in a neural network model.
Plain in plain English.
The landmark embedding class is defined, which is a custom layer for landmark embeddings in TensorFlow. Inside the underscore underscore init underscore underscore method, the constructor, two parameters are defined, number underscore hit and max len. Number underscore hit represents the hidden dimension of the embedding outputs, and max len represents the maximum sequence length. The super dot underscore underscore init underscore underscore line initializes the base class, layers, layer, using its constructor. The class has three attributes, self.conv1, self.conv2, and self.conv3, which are instances of the conv1d layer in TensorFlow. These convolutional layers perform 1D convolution operations on the input. They have number underscore hit filters, an 11 length kernel size, a stride of 2, same padding, and use the ReLU activation function. The last attribute, self.cos underscore emb, is an instance of the embedding layer from layers. It is used for positional encoding, mapping the position indices of tokens in a sequence to hidden dimensional vectors. The input underscore dim is set to max len, which represents the maximum sequence length, and the output underscore dim is set to number underscore hit. The landmark embedding class combines convolutional layers, self.conv1, self.conv2, and self.conv3, with positional embeddings, self.cos underscore emb, to generate landmark embeddings. This class can be used as a building block for models that require landmark representations, such as in computer vision tasks or sequence processing tasks.
Okay. Explain to what? To, let's say, final year engineering student.
As a final year engineering student, understanding the code snippet and its implications can be important for your studies. Let's break it down in simpler terms. The landmark embedding class represents a custom layer designed to generate landmark embeddings. Think of this class as a special function that performs specific operations on data. Inside the underscore underscore init underscore underscore method, the constructor, two parameters are defined, number underscore hit and max len. These parameters determine the size and characteristics of the embeddings. The super dot underscore underscore init underscore underscore line initializes the base class, layers, layer. It ensures that the functionalities and features provided by the base class are available to the landmark embedding class. The class has three convolutional layers, self.conv1, self.conv2, and self.conv3. These layers take the input data and perform operations called convolutions to extract meaningful features. The number of filters in each convolutional layer is determined by number underscore hit, and the operations are carried out with an 11 length kernel, a stride of 2, moving in steps of 2, same padding, preserving the input size, and the ReLU activation function, which introduces nonlinearity. The last attribute, self.cos underscore emb, represents an embedding layer. Embedding is a technique used to convert categorical data, such as position indices, into meaningful numerical representations. The embedding layer maps position indices to hidden dimensional vectors. The input underscore dim is set to max len, which represents the maximum sequence length, and the output underscore dim is set to number underscore hit. In summary, the landmark embedding class combines convolutional layers with positional embeddings to generate landmark embeddings. These embeddings can be useful in various applications, such as computer vision tasks or sequence processing tasks. As a final year engineering student, understanding concepts related to deep learning, neural networks, and layers can provide you with a solid foundation for machine learning and data analysis, which are valuable skills in today's technology-driven world.
Yeah, that's right. Explain the terms. So I was still training anyway. Yeah, reached 2.6 loss function. It's only 3 out of 15 epochs, so this might take a while. Might get back to it later. But in the meantime, there's a few questions that we trying to answer. First, how do we set up all the layers in the model, neural network model? And then how do you choose what these parameters should be, except trial and error?
Class. A class is a blueprint or template for creating objects in object-oriented programming. It defines the properties, attributes, and behaviors, methods, that objects of that class will have. Layer. A layer is a fundamental component in deep learning models. It performs specific operations on the input data, such as transformations, computations, or feature extraction. Landmark embedding. Landmark embedding is the name of the class being defined in the code. It represents a custom layer that performs operations to generate landmark embeddings. Init __init__ is a special method, constructor, in Python classes that is automatically called when an object of the class is created. It initializes the attributes and sets their initial values. Number_hid. Number_hid is a parameter/argument of the class's constructor. It represents the hidden dimension or the number of hidden units/neurons in the embedding outputs. Maxlen. Maxlen is another parameter/argument of the constructor. It represents the maximum sequence length, which is the maximum number of elements in a sequence. Super is a built-in function that allows access to the methods and attributes of the parent/base class. In this case, it calls the __init__ method of the parent class, layers, layer, to initialize it. CONV1D. CONV1D is a class from the tf.keras.layers module. It represents a one-dimensional convolutional layer, which performs convolution operations on the input data. It extracts features by sliding a window/kernel over the input. Padding. Padding is a parameter of the CO. Represents a one-dimensional convolutional layer, which performs convolution operations on the input data. It extracts features by sliding a window/kernel over the input. Padding. Padding is a parameter of the CONV1D layer. It determines how the input is padded to ensure that the output has the same length as the input. In this case, same padding is used, which adds padding equally to both ends. Activation. Activation is a parameter of the CONV1D layer that specifies the activation function applied to the outputs of the convolutional layer. In this case, the ReLU, rectified linear unit, activation function is used, which introduces nonlinearity. POS_EMB. POS_EMB is an attribute of the class. It represents an instance of the embedding layer from the layers module. It is used for positional encoding, mapping position indices to hidden dimensional vectors. Embedding. Embedding is a class from the layers module. It represents an embedding layer that converts categorical data, such as position indices, into numerical representations. It maps discrete values to continuous vectors. These explanations should provide you with a better understanding of each term and its role in the code snippet.
How to select parameters values? I'm talking about these specific parameters. Hopefully it will understand. Right. No, it's not quite like generic. I actually meant those. Like the essentially explain the magic numbers. But this is actually interesting, so we will read it.
Selecting appropriate parameter values for a machine learning model is an important step in achieving good performance and efficient training. Here are some general guidelines and strategies for selecting parameter values. Domain knowledge. Having a good understanding of the problem domain and the characteristics of the data can guide your parameter selection. Consider the nature of the problem, the type of data, and any specific constraints or requirements. Literature and research. Research papers, articles, and online resources related to your problem domain and specific model architectures can provide insights into commonly used parameter values. Look for established best practices and recommendations. Hyperparameter tuning. Hyperparameter tuning techniques can help you systematically search for optimal parameter values. Methods such as grid search, random search, and Bayesian optimization can be employed to explore the parameter space and find the best combinations. Tools like scikit-learn's grid search CV or libraries like Optina and Keras Tuner can assist in this process. Experimentation and evaluation. Perform experiments with different parameter values and evaluate the model's performance. Use appropriate evaluation metrics to measure the model's effectiveness. Compare the results obtained with different parameter settings to identify the ones that yield the best performance. Start with default values. Most machine learning frameworks provide default values for various parameters. These defaults are often chosen to work reasonably well for a broad range of problems. Begin with these default values and iterate from there based on experimentation and evaluation. Learning rate. The learning rate is a crucial hyperparameter in optimization algorithms. It controls the step size during model training. Consider starting with a moderate learning rate and adjust it based on the observed training dynamics, example, if the loss is not decreasing or if the model is diverging. Cross-validation. When evaluating parameter values, use techniques like cross-validation to assess model performance on multiple folds of the data. This helps to account for variations in the data and provides a more reliable estimate of model performance. Prioritize key parameters. Identify the most influential parameters for your specific problem and prioritize.
That got to 0.6 loss function. Oh, so that's for the training set. Yeah, they're going down at the same rate. And actually validation is a bit lower this time. This is not what we had previously. So that's for the 80-20 split. And they were, what's it, at 0.6? Now it's for both 0.66. So around, this is epoch 3. Right, so they're about at that point. And we see if it makes any difference. In theory, I would expect them both to go down at the same rate, considering the two datasets should be essentially the same. But we will see how that goes.
Cross-validation. When evaluating parameter values, use techniques like cross-validation to assess model performance on multiple folds of the data. This helps to account for variations in the data and provides a more reliable estimate of model performance. Prioritize key parameters. Identify the most influential parameters for your specific problem and prioritize their tuning. Focus on parameters that significantly impact model performance rather than fine-tuning all parameters at once, as it can be time-consuming and less effective. Keep track of experiments. Maintain a record of the parameter settings used in each experiment along with the corresponding results. This documentation helps in analyzing the effects of different parameter choices and serves as a reference for future work. Remember that parameter selection is often an iterative process, and it may require multiple iterations to find the optimal values. It's important to strike a balance between exploring different values and avoiding excessive parameter tuning, as overfitting to the validation set can occur. By combining a systematic approach, experimentation, and domain knowledge, you can select parameter values that work well for your specific problem and dataset.
Yeah, that's fine. That edit distance doesn't seem to change much. That's not what we asked it to do. I was actually asking about the specific parameters. It started giving me all sort of generic stuff. That's okay. This is where we were. Want to explain. This should be fairly straightforward.
The call method is a function within a class, commonly used in deep learning frameworks like TensorFlow to define the forward pass or inference logic of a model. It takes an input x as its argument. X equals self.conv1 x applies the conv1 layer to the input x. This means that the input x is passed through the first convolutional layer, conv1, defined in the class. The result of this operation is stored back into x.
Actually, this one, the tab 9 thing is giving errors. Is this even correct? And what? No. Yeah, it's not as good as GitHub Copilot, as in getting the embedding output. Well, maybe we'll say the same. Want to add something more, is it? No. And here it's suggesting to add something to the code. Like, no. Get the embedding output position on code there. Solution 3. That's pretty sure that's wrong, is it?
X equals self.conv2 x applies the conv2 layer to the updated x. This means that the updated x is passed through the second convolutional layer, conv2, defined in the class. The result of this operation is stored back into x. Return self.conv3 x applies the conv3 layer to the final updated x and returns the result. This means that the updated x is passed through the third convolutional layer, conv3, defined in the class. The output of this operation is the final result of the call method. In summary, the call method applies 3 convolutional layers, CONV1, CONV2, and CONV3, to the input X in sequence. Each convolutional layer applies specific operations, such as filtering and feature extraction, to transform the input. The final output is the result of passing the input through the third convolutional layer, CONV3. This call method encapsulates the forward pass of the model, where the input flows through the defined layers to produce an output.
This was originally GitHub Copilot suggested. Why is it apologizing and then giving you snippets of code? Just the same?
Apologies for the oversight. You are correct. Let's provide an updated explanation.
What? Why?
The call method is part of a class and serves as the forward pass for a model. It takes an input X as its argument, which represents the landmarks data.
What it said before?
Applies the first convolutional layer, CONV1, to the input X. Convolutional layers are commonly used in deep learning for feature extraction. By passing the input X through CONV1, the layer applies the second convolutional layer, CONV2, to the updated X. This step continues the feature extraction process, refining the extracted features further. The output of CONV2 is stored back into X. Applies the third convolutional layer, CONV3, to the final updated X and returns the result. Similar to the previous steps, CONV3 applies operations to further extract features from the refined input X. The output of CONV3 is the final result of the call method. The overall purpose of these convolutional layers is to extract meaningful features from the landmarks data. Each convolutional layer applies a set of filters and operations to the input, transforming it into a representation that captures important information from the landmarks. These extracted features can be subsequently utilized by other layers or parts of the model for tasks such as classification or regression. Additionally, as mentioned in your updated explanation, the code snippet you provided may also involve a positional encoding layer. However, based on the given code, it is not explicitly present in the call method. If the positional encoding layer exists in the overall model definition outside of this call method, it would be used to incorporate information about the relative positions of the landmarks in the sequence.
Okay. Encode a layer for transformer. Sorry, we already did this before with GitHub Copilot. Now we're doing it again. It was actually quite good. One sec.
The code snippet you provided defines a class called transformer encoder. It represents a single layer of a transformer-based neural network architecture. Let's break it down. The transformer encoder class is defined, representing a single transformer encoder layer. The __init___ method is the constructor of the class. It takes several parameters. Embed_dim, the embedding dimension, which represents the size of the input and output vectors. Number_heads, the number of attention heads to use in the multi-head attention mechanism. Feed_forward_dim, the dimension of the feed forward layer. Rate, the dropout rate to apply after each sublayer. Self.att is an instance of the multi-head attention layer from the layers module. It performs multi-head self-attention on the inputs. The number_heads parameter determines the number of attention heads, and the key_dim parameter specifies the dimensionality of the key vectors. Self.ffn is a feed-forward network implemented as a sequential model from Keras. It consists of 2 dense layers. The first dense layer has feed_forward_dim units with ReLU activation, and the second dense layer outputs vectors with a dimensionality of embed_dim. Self.layernorm1 and self.layernorm2 are instances of the layer normalization layer from the layers module. They perform layer normalization on the inputs. Self.dropout1 and self.dropout2 are instances of the dropout layer from the layers module. They apply dropout regularization to the inputs with a rate specified by rate. Python. Copy code. Def call, self, inputs, training attention underscore output equals self.att, inputs, inputs, attention underscore output equals self.dropout1, attention underscore output, training equals training, out1 equals self.layer norm1, inputs plus attention underscore output, ffn underscore output equals self.ffn, out1, ffn underscore output equals self.dropout2, ffn underscore output, training equals training, return self.layer norm2, out1 plus ffn underscore output. The call method defines the forward pass logic of the transformer encoder layer. Inputs is the input to the layer. Training is a Boolean flag indicating whether the model is in training mode or not. Attention underscore output performs multi-head self-attention on the inputs. Out1 adds the inputs and attention underscore output and applies layer normalization. FFN underscore output passes out1 through the feed-forward network, self.ffn. Out1 plus FFN underscore output adds out1 and FFN underscore output. The final output is obtained by applying layer normalization to the sum of out1 and FFN underscore output. In summary, the transformer encoder class represents a single layer of a transformer model. It consists of a multi-head self-attention mechanism, a feed-forward network, layer normalization, and dropout regularization. The call method defines how the inputs are processed through these components to produce the final output. Free research preview. ChatGPT may produce inaccurate information about people, places, or
Sorry for that. Explain. In plain English. Final year engineering student. How about first year?
the code defines a class called transformer encoder, which represents a single layer in a transformer-based neural network. The underscore underscore init underscore underscore method is a special method that is automatically called when an object of the class is created. It initializes the attributes of the class. Here, it takes several parameters. Embed underscore dim, it represents the size of the input and output vectors. Number underscore heads, it determines the number of attention heads used in a layer. Feed underscore forward underscore dim, it specifies the size of the feed forward layer. Rate, it determines the dropout rate, which is a form of regularization to prevent overfitting. Self.att is an instance of the multi-head attention layer. It performs multi-head self-attention, which is a mechanism that helps the model focus on different parts of the input during training. It takes the number of heads, number underscore heads, and the dimension of the key vectors, key underscore dim, as parameters. Self.ffn is a sequential model, a sequence of layers, that consists of two dense layers. Dense layers are fully connected layers that perform mathematical operations on the input data. The first dense layer has feed underscore forward underscore dim units and uses the ReLU activation function. The second dense layer outputs vectors with a dimensionality of embed underscore dim. Self.layer norm1 and self.layer norm2 are instances of the layer normalization layer. They perform layer normalization, which helps in stabilizing and normalizing the outputs of the layer. Self.dropout1 and self.dropout2 are instances of the dropout layer. Dropout is a regularization technique that randomly sets a fraction of input units to 0 during training, which helps prevent overfitting. Python. Copy code. Def call, self, inputs, training attention underscore output equals self.att, inputs, inputs, attention underscore output equals self.dropout1, attention underscore output, training equals training, out1 equals self.layer norm1, inputs plus attention underscore output, ffn underscore output equals self.ffn, out1, ffn underscore output equals self.dropout2, ffn underscore output, training equals training, return self.layer norm2, out1 plus ffn underscore output. The call method defines the forward pass of the transformer encoder layer. Inputs represents the input to the layer. Training is a Boolean flag that indicates whether the model is in training mode or not. Attention underscore output applies multi-head self-attention to the inputs, focusing on different parts of the input during training. Out1 adds the inputs and attention underscore output together and performs layer normalization. The final output is obtained by performing layer normalization on the sum of out1 and ffn underscore output. In summary, the transformer encoder class represents a single layer of a transformer model. It includes self-attention, feed-forward operations, layer normalization, and dropout. The call method describes how the input data flows through these operations to produce the final output of the layer.
Feels to me like a lot of these magic numbers would just default or trial and error. Now, if you say have these annotations here and you put it in GPT, do you then bias it? That already understands that I'm trying to break out the code, which is good.
The transformer decoder class represents a single layer of the transformer decoder in a transformer-based neural network. The underscore underscore init underscore underscore method is the constructor of the class. It initializes the attributes of the class. Here, it takes several parameters. Embed underscore dim, the embedding dimension, representing the size of the input and output vectors. Number underscore heads, the number of attention heads to use in the multi-head attention mechanisms. Feed underscore forward underscore dim, the dimension of the feed forward layer. Dropout underscore rate, the dropout rate to apply after each sublayer. Self.layer norm 1, self.layer norm 2, and self.layer norm 3 are instances of the layer normalization layer. They perform layer normalization on the inputs. Self.self underscore ATT is an instance of the multi-head attention layer that performs self-attention within the decoder layer. It takes the number of attention heads, number underscore heads, and the dimension of the key vectors, key underscore dim, as parameters. Self.enc underscore ATT is an instance of the multi-head attention layer used to attend over the encoder outputs. It also takes the number of attention heads, number underscore heads, and the dimension of the key vectors, key underscore dim, as parameters. Self.self underscore dropout, self.enc underscore dropout, and self.ffn underscore dropout are instances of the dropout layer. They apply dropout regularization with specific dropout rates to the inputs during training to prevent overfitting. Self.ffn is a sequential model consisting of two dense layers. It performs feed-forward operations on the inputs, transforming them into a higher dimensional space and then back to the original embedding dimension. They apply dropout regularization with specific dropout rates to the inputs during training to prevent overfitting. Self.ffn is a sequential model consisting of two dense layers. It performs feed-forward operations on the inputs, transforming them into a higher dimensional space and then back to the original embedding dimension. Python. Causal underscore attention underscore mask is a helper method that generates a mask to prevent information flow from future tokens to the current token during self-attention. It creates a triangular mask matrix with ones in the lower triangle and zeros in the upper triangle. Python. A helper method that generates a mask to prevent information flow from future tokens to the current token during self-attention. It creates a triangular mask matrix with ones in the lower triangle and zeros in the upper triangle.
What did the thing originally said?
Masking the upper half of the dot product matrix in self-attention hashtag to prevent flow of information from future tokens to current token. Hashtag it sets ones in the lower triangle, counting from the lower right corner. Hashtag returns the mask.
What? Didn't I ask to explain to undergrad student?
The call method defines the forward pass logic of the transformer decoder layer. Enc underscore out represents the encoder outputs, and target represents the inputs to the decoder layer. Input underscore shape determines the shape of the target input tensor. Causal underscore mask is created using the causal underscore attention underscore mask method to prevent attending to future tokens. Target underscore ATT performs self-attention on the target using the self underscore ATT layer and applies the causal underscore mask. In summary, the transformer decoder class represents a single layer of the transformer decoder in a transformer-based neural network. It includes self-attention, multi-head attention with encoder outputs, feed-forward operations, layer normalization, and dropout regularization. Did
it just stop generating or? Oops. No. Lane. Final year. And we said explain the first year engineer student. No one else. Lay person.
The code you provided defines a class called Transformer Decoder. This class represents a building block of a larger model called a transformer. Transformers are commonly used in machine learning for tasks like language translation, text generation, and image processing. The Transformer Decoder class is responsible for processing information and making predictions based on the inputs it receives. It performs several operations on the input data to transform and extract meaningful information. Here's a simplified explanation of what the code does. The __init___ method sets up the initial configuration of the Transformer Decoder object. It defines various components such as normalization layers, attention mechanisms, and dropout layers. These components help in processing and transforming the data effectively. The call method is where the actual processing happens. It takes the input data and performs a series of steps to generate the output. Here's a breakdown of what each step does. It calculates the shape of the input data. It creates a mask that ensures the model only looks at previous information and prevents it from seeing into the future. It applies self-attention to the input data, which allows the model to focus on different parts of the input while considering the context. It applies normalization to the output of the self-attention step. It combines the output from the self-attention step with information from the encoder, another part of the model, using multi-head attention. This allows the model to consider both the input and the previously processed information from the encoder. It applies normalization to the output of the multi-head attention step. It passes the output through a feed-forward neural network, which performs additional transformations on the data. It applies normalization to the output of the feed-forward step. The final result is the transformed and processed output. In simpler terms, the Transformer Decoder class takes input data, performs various operations on it to understand the context and extract meaningful information, and then generates an output based on that processed information. Overall, transformers and their components, like the Transformer Decoder class, are powerful tools for processing and understanding complex data, enabling machines to perform tasks like language translation or image recognition. Free research preview. ChatGPT may
It's either too specific or too general. Which is a bit of a problem. Right, we would complete the transformer model. It's the Keras model. Yeah, this one has almost no annotations, which is good. It's the last line is return tag input. That's right. Break it down. Explain to a lay person in simple terms.
Overall, the transformer class encapsulates the architecture and functionality of a transformer model for a specific task, including the encoding, decoding, training, evaluation, and inference steps. Explain to a layperson in simple terms. ChatGPT. Let's explain the code snippet to a layperson. The code you provided defines a class called Transformer Decoder. This class represents a building block of a larger model called a transformer. Transformers are commonly used in machine learning for tasks like language translation, text generation, and image processing. The Transformer Decoder class is responsible for processing information and making predictions based on the inputs it receives. It performs several operations on the input data to transform and extract meaningful information. Here's a simplified explanation of what the code does. The __init___ method sets up the initial configuration of the Transformer Decoder object. It defines various components such as normalization layers, attention mechanisms, and dropout layers. These components help in processing and transforming the data effectively. The call method is where the actual processing happens. It takes the input data and performs a series of steps to generate the output. Here's a breakdown of what each step does. It calculates the shape of the input data. It creates a mask that ensures the model only looks at previous information and prevents it from seeing into the future. It applies self-attention to the input data, which allows the model to focus on different parts of the input while considering the context. It applies normalization to the output of the self-attention step. It combines the output from the self-attention step with information from the encoder, another part of the model, using multi-head attention. This allows the model to consider both the input and the previously processed information from the encoder. It applies normalization to the output of the multi-head attention step. It passes the output through a feed-forward neural network, which performs additional transformations on the data. It applies normalization to the output of the feed-forward step. The final result is the transformed and processed output. In simpler terms, the Transformer Decoder class takes input data, performs various operations on it to understand the context and extract meaningful information, and then generates an output based on that processed information. Overall, transformers and their components, like the transformer decoder class, are powerful tools for processing and understanding complex data, enabling machines to perform tasks like language translation or image recognition. Class transformer, chars, model def underscore underscore. The code you provided defines a class called transformer, which represents a type of machine learning model. This model is designed to solve a specific task, such as language translation or text generation. Let's break down the important parts in simpler terms. The transformer class has attributes that keep track of the model's performance during training and testing. These attributes help measure how well the model is learning and making predictions. The class has parameters that control the size and complexity of the model. These parameters determine how the model processes and transforms data to make predictions. The underscore underscore init underscore underscore method is called when a new transformer object is created. It sets up the initial configuration of the model. It creates different parts of the model, such as embedding layers and encoder/decoder layers. These components help the model understand and manipulate the input data. The decode method takes the encoded input data and generates the output based on the learned patterns. It uses a decoder layer to transform the encoded input into a meaningful output. The call method is the main function that processes the input data through the model. It uses the encoder layers to understand the input and the decoder layers to generate the output. The output is then passed through a classifier layer to make a final prediction. The train underscore step method is used during the training phase. It takes a batch of training data, calculates the difference between the predicted output and the actual output, and adjusts the model's internal parameters to minimize this difference. This helps the model improve its predictions over time. The test underscore step method is used during the testing phase. It evaluates how well the model performs on a separate set of test data. It calculates the difference between the predicted output and the actual output to measure the model's accuracy. The generate method is used for making predictions on new data. It takes input data and generates an output sequence using the learned patterns. It does this by sequentially generating each part of the output based on the previous parts. In simpler terms, method is used for making predictions on new data. It takes input data and generates an output sequence using the learned patterns. It does this by sequentially generating each part of the output based on the previous parts. In simpler terms, the transformer class represents a machine learning model that can understand and generate sequences of data. It learns from examples during training, adjusts its internal parameters to make accurate predictions, and can generate new sequences based on what it has learned.
Let's do a few more and we will say bye-bye for now. It's in yellow hand, red-handed. And we'll just might have an hour, like 15 minutes or so to keep going. We'll just keep explaining the code with GPT. We're still training the model. It might take some time to retrain it. And I'll let you know how it goes. Bye for now. Simplify the explanation of the whole code so far so that a high school student can understand.
The code you provided defines a special type of computer program called a transformer model. This model is used for tasks like language translation or text generation. The transformer model is designed to process and understand sequences of data, like sentences or paragraphs. The transformer class represents this model and has different parts that work together. The model has a way to measure how well it's doing, just like a student has a grade for a test. It keeps track of its performance during training and testing. The model has different settings that determine its complexity, like the size of the model and the number of calculations it can do. These settings affect how the model understands and generates the output. The underscore underscore init underscore underscore method is like setting up.
Can we simplify the whole code? So yes, so far, so that the high school student can understand. Use sign language data processing as example. Language a finger location coordinates data processing.
The code you provided represents a model that can understand and generate sign language gestures based on finger coordinates. Here's a breakdown in simpler terms. The transformer model is like a smart system that learns to understand and generate sign language gestures. It takes in finger coordinate data as input and produces meaningful gestures as output. The model has an encoder part that learns to understand the finger coordinate data. It looks at the input coordinates and tries to capture patterns and relationships between them. The model also has a decoder part that generates the corresponding sign language gesture based on what it learned from the encoder. It uses this knowledge to predict the most likely gesture that matches the finger coordinates. During training, the model learns by comparing its predicted gestures with the correct gestures in the training data. It adjusts its internal parameters to minimize the difference between its predictions and the actual gestures. The model is evaluated using a separate set of test data to see how well it can generate accurate sign language gestures. It measures how closely its predicted gestures match the actual gestures. Once the model is trained and evaluated, it can be used to generate sign language gestures for new finger coordinate data. It takes the finger coordinates as input, processes them through the encoder and decoder, and produces the corresponding sign language gesture as output. In summary, the code represents a model that learns to understand and generate sign language gestures based on finger coordinates. It goes through a process of learning, evaluation, and prediction to achieve this. The goal is to create a system that can help people communicate using sign language more effectively.
Sign language finger coordinates. Yeah, this one a recognition. What's the last code snippets we had? Yeah, this one. Let's do this next one. Read that in a sec. So supposedly it keeps all the context in place, but yeah, I'm still trying to understand how well it's doing it.
Let's simplify the explanation of the code in the context of sign language finger coordinates data recognition so that a high school student can understand. The code you provided represents a machine learning model called a transformer, which is used to recognize sign language finger coordinates. Here's how it works. Imagine you have a dataset of sign language finger coordinates, where each sign is represented by a sequence of finger positions. The transformer model is designed to learn patterns from these finger coordinates and predict the corresponding sign language gesture. The model consists of an encoder and a decoder. The encoder takes the input finger coordinates and processes them to capture important information. The encoder uses an embedding layer to convert the finger coordinates into a meaningful representation. It then applies multiple encoder layers to understand the sequence and extract useful features. The decoder takes the encoded finger coordinates and generates a sequence of predicted finger coordinates, which represent the sign language gesture. The decoder also uses an embedding layer and multiple decoder layers. It attends to the encoded finger coordinates and generates the predicted gesture based on the learned patterns. During training, the model learns from examples by comparing its predicted gestures with the actual gestures in the dataset. It adjusts its internal parameters to minimize the difference between the predictions and the actual gestures. The model also measures its performance using metrics such as loss, which measures the model's prediction accuracy, and edit distance, which measures the difference between predicted and actual gestures. The model is trained using a training step, where it processes batches of finger coordinates and updates its parameters based on the difference between the predictions and the actual gestures. Similarly, the model is evaluated using a testing step, where it measures its performance on separate test data to see how well it generalizes to unseen examples. After training, the model can be used for inference. Given new finger coordinates, it can generate the predicted sign language gesture by sequentially generating each part of the gesture based on the previous parts. In summary, the transformer model learns patterns from sign language finger coordinates to predict corresponding gestures. It consists of an encoder and a decoder, which process the coordinates and generate predictions. The model is trained and evaluated using training and testing steps, and it can be used to recognize sign language gestures in real time by making predictions based on new finger coordinates. Class display outputs, chars.callbacks, callback def underscore underscore init underscore underscore, self, batch, idx underscore to underscore token, target underscore start. The code you provided defines a custom callback class called display outputs. This callback is used during training to display the model's outputs after every 4 epochs. Here's a simplified explanation of what the code does. In simple terms, the display outputs callback class is used to show the model's predicted outputs compared to the expected outputs during training. It does this by generating predictions based on the input data and displaying the predicted and target text side by side for visual inspection. This helps monitor the model's progress and check if it is learning to generate the desired outputs.
So I didn't quite get it. It's only generated I did some testing in the beginning. Would it do them after training as well? Yeah, some of this explanations are not great at all. This is what it did last time, this time 0.5. 0.57. Yeah, the validation loss is significantly higher. So yes, the opposite of diverge, they're not diverging. Anyway, that's the last snippet where I think we have last yeah, that gives us no GPUs found. I don't know why. We have to fix that. Then we have this code. This code sounds like he's saying disco, but not really.
The code you provided first checks if a model checkpoint file, model_checkpoint, exists. If the checkpoint file does not exist, it proceeds with training and saves the trained model. Otherwise, it loads the pre-trained model from the checkpoint file. Here's a simplified explanation of what the code does. The model_checkpoint variable contains the file path where the model will be saved or loaded from. The code checks if the model_checkpoint file exists using the os.path.exists function. If the file does not exist, it means that the model has not been trained yet. If the model_checkpoint file does not exist, the code proceeds with training the model. It first retrieves a batch of data from the validation dataset, valid_ds, using the next function. The code creates an instance of the display outputs callback class, passing the batch of data, the mapping of indices to characters, and the start/n token indices for the target vocabulary. The code initializes a new instance of the transformer model, specifying various parameters such as the hidden dimension, number of attention heads, and number of layers. The loss function and optimizer are defined for the model. The loss function is set to categorical cross entropy, which calculates the loss between the predicted and target outputs. The optimizer is set to Adam with a learning rate of 0.0001. The model is compiled by specifying the optimizer and loss function. The fit method is called on the model, providing the training dataset, train_ds, and validation dataset, valid_ds, as input. The fit method trains the model for a specified number of epochs, and the display outputs callback is passed as a callback to visualize the outputs during training. After training, the trained model is saved to the model_checkpoint file using the save method. If the model_checkpoint file already exists, it means that a pre-trained model is available. The code loads the model from the checkpoint file using the load_model method. In simple terms, the code checks if a trained model is already saved. If not, it trains a new model using the provided datasets and saves it. If a trained model is already saved, it loads the pre-trained model for further use without training again. This allows you to continue training a model or use a pre-trained model for inference. During training, the code keeps track of the model's progress and displays the predicted outputs alongside the expected outputs every few epochs. The trained model is
So that's done every 4 epochs. So in theory, next epoch it will do this again. Predicted the outputs alongside the expected outputs.
The trained model is then saved to a file so that it can be reused later. If the model file already exists, it means a trained model is available. In this case, the code loads the pre-trained model from the file. In simpler terms, the code either trains a new model from scratch or loads an existing trained model. The model is trained using a dataset, and during training, the code displays the model's predictions. After training, the model is saved to a file for future use. If a saved model already exists, the code loads it for use. During the first epoch of training, the model processed a total of 632 batches. Each batch took approximately 630 seconds, or 10.5 minutes, to process. The model achieved a loss value of 0.8796 and an edit distance value, a measure of prediction accuracy, of 1.0590. Here are a couple of examples showing the target text. An edit distance value, a measure of prediction accuracy, of 1.0590. Here are a couple of examples showing the target text, the expected output, and the corresponding prediction generated by the model. In these examples, the model attempted to generate the predicted output based on the input data. However, the predictions don't match the expected targets very closely. The model needs further training to improve its accuracy and generate more accurate predictions.
So what's this number? Is it a high? It's the range. Keeps apologizing if you copy paste something it already said.
Apologies for the confusion in my previous response. The edit distance is typically a non-negative integer value that measures the dissimilarity between two strings. It represents the minimum number of operations, insertions, deletions, substitutions, required to transform one string into another. In the given context, an edit distance value of 1.0590 doesn't make intuitive sense since edit distance should be an integer. It's possible that the value reported is a floating point representation or a rounded value. In general, a lower edit distance indicates a higher similarity between the predicted output and the target output. Lower edit distance indicates a higher similarity between the predicted output and the target output. A value of 0 would mean a perfect match between the predicted and target outputs.
So this value doesn't change much.
Please note that the specific interpretation of the edit distance value in the provided code may depend on how it is calculated or reported within the implementation. During the training process, the model processed a total of 632 batches. The progress is indicated as 632/632, meaning it has completed training on the entire dataset. The training metrics for the last batch of the training set are as follows. Loss, 0.5500, a value that represents the difference between the predicted output and the target output. Edit distance, 1.0350, a measure of dissimilarity between the predicted and target outputs. These metrics indicate how well the model is learning during training. A lower loss value and edit distance indicate better performance and closer predictions to the target outputs. Additionally, the validation metrics are also reported. Validation loss, 0.5861. Validation edit distance, 1.0339. These metrics provide an evaluation of the model's performance on a separate validation dataset. The validation loss and edit distance provide insights into how well the model generalizes to unseen data. Overall, the model is making progress in reducing the loss and edit distance during training, and the validation metrics give an indication of its performance on unseen data.
Question is, to make sign language prediction better, do I retrain this model or create a new one?
To improve sign language prediction, you have a couple of options: retraining the existing model or creating a new one. Here's some guidance on each approach. Retraining the existing model. If the existing model is not performing well and you have a large dataset, you can consider retraining the model. You can gather more training data, especially if you have a limited dataset, to provide the model with more examples to learn from. Experiment with different hyperparameters, such as the number of layers, hidden units, or learning rate, to see if any adjustments lead to better performance. You can also try different loss functions or regularization techniques to improve the model's ability to generalize. Creating a new model. If the existing model architecture seems inadequate for the complexity of the sign language recognition task, you might want to explore different model architectures. Look into state-of-the-art models specifically designed for sign language recognition, such as those utilizing convolutional neural networks, CNNs, or recurrent neural networks, RNNs. Consider leveraging pre-trained models or transfer learning techniques, where you can use a model pre-trained on a large dataset and fine-tune it for sign language recognition. Ultimately, the decision to retrain or create a new model depends on various factors, including the amount and quality of available data, the performance of the current model, and the specific requirements of your sign language recognition application. Experimentation, careful evaluation, and iterative improvements are key in achieving better prediction results.
Let's ask a GPT that is connected to the internet about models specifically designed for sign language recognition.
Sign language is the primary means of communication used by deaf and dumb people. Learning this language could be perplexing for humans, therefore, it is critical to develop a system that can accurately detect sign language. The fields of deep learning and computer vision with recent advances are used to make an impact in sign language recognition with a fully automated deep learning architecture. This paper presents two models built using two deep learning algorithms, VGG16 and convolutional neural network, CNN, for recognition and classification of hand gestures. The project aims at analyzing the model's performance quantitatively by optimizing accuracy obtained using limited dataset. It aims at designing a system that recognizes the hand gestures of American Sign Language and detects the alphabets. Both the models gave excellent results, VGG16 being the better. VGG16 model delivered an accuracy of 99.56% followed by CNN with an accuracy of 99.38%.
This article, yeah, very odd. This, what was it? Generated by a language model or something, because it doesn't seem like a human will write anything like this. Like the first sentence. And yeah, the performance is pretty good. The paper's behind a paywall. We can still try and get it. I'll do that later. Because some of the tools, my tools of getting papers might not be 100%. But yeah, that accuracy 99.56%. Yeah, it's pretty good. This is a conference. Yeah, it's odd that it's picking up a conference. Wikipedia. Sign language recognition models.
An American Sign Language Recognition system with flex and motion sensors was implemented in Ref. 1. This system produced better results than a cyber glove embedded with a Kinect camera. Authors succeeded in proposing a model which performs better recognition of signs using different algorithms of machine learning. 2. Response time and accuracy were increased using better sensors and an efficient algorithm for the specified task. The traditional approach of sign language was changed by embedding sensor networks for recognition purposes. A proposed model was implemented by the combination of artificial neural network (ANN) and support vector machine (SVM) in sign language recognition. This combined algorithm produced better results than the hidden Markova model (HMM). 3. A smart data glove named eVoice was developed by authors for alphabetical gesture recognition of ASL. The prototype was designed using flex sensors and accelerometer sensors. The data glove was successful in recognizing sign gestures with improved accuracy and increased efficiency. 4. Sign language is a subjective matter, so a new method of recognition was developed using surface electromyography (SEMG). Here, sensors were connected to the right forearm of the subject and collected data for training and testing purposes. They used the support vector machine (SVM) algorithm for recognition and obtained better results for real-time gesture recognition. 5. Another model was proposed as a combination of 3 types of sensors. These sensors included flux, motion, and pressure sensors to determine SVM impact on sign language recognition. 6. Daily activity was recognized using a smart data glove. 2 basic techniques for gesture interpretation were used using data glove interaction. 7. Implementation of a more advanced approach including a deep learning model was developed in Ref. 8. Static gestures were converted into American Sign Language alphabets using Hoff transform, and this technique was applied on 15.
So our data is different. Therefore, whatever a model training or whatever they did used might not work for us because the data is very different. Our data is the location of the digits in space.
15 samples per alphabet and obtained 92% accuracy. A combination of motion tracker and the smart sensor was used in sign language recognition. An artificial neural network approach was implemented to obtain the desired results. 9. The artificial neural network translates American Sign Language into alphabets. A sensory glove called a smart hand glove with a motion detection mechanism was used for data collection purposes, and as a result, the transmitter-receiver network processed input data to control home appliances and generate recognition results. 10. Hand-body language-based data analysis was performed using a machine learning approach. A sensor glove embedded with 10 sensors was used to capture 22 different kinds of postures. KNN, SVM, and PNN algorithms were applied to perform sign language posture recognition. 11. The authors in Ref. 12. Presented a device named the electronic speaking glove. This device was developed using a combination of flex sensors. Flex sensor data were fed into a low-power, high-performance, and fast 8-bit Mega 32L AVR microcontroller. A reduced instruction set architecture, RISC-based AVR microcontroller used the template matching algorithm for sign language recognition. Another sign language recognition-based system was developed by 13. This virtual image interaction-based sensor system succeeded in recognizing 6 letters, i.e., A, B, C, D, F, and K, and a digit, 8. So, the prototype was developed using 2 flex sensors attached to the index and middle finger of the right hand. These sensor data were transmitted towards the Arduino Uno microcontroller. In this experiment, the advanced, intelligent, and smart system was implemented by the authors in Ref. 16. Their experimental setup included 8 contact sensors and 9 flex sensors. These sensors were placed inside and outside of fingers. The outer 5 sensors were deployed to detect bending changes, and the inner 4 sensors were attached to measure hand orientation. This system was also based on a template matching algorithm where a unique 36 gesture-based standard ASL dataset was matched with input data. The 8 Mega 328P microcontroller was used for matching purposes, which succeeded in producing 83.1% and 94.5% accuracy for alphabet and digits, respectively. In Ref. 17, the authors made a standard sign language recognition prototype. This prototype consisted of 5 flex sensors embedded with an 8 Mega 328-based microcontroller. Senior-based acquired data were compared with the already stored ASL dataset. This experimental set succeeded in producing 80% overall accuracy. To facilitate the deaf-mute community, another important contribution was presented by Ref. 18. The author succeeded in developing a prototype which translates sign language into its perfectly matched alphabet or digit. 11 resistive sensors were used to measure the bending of each finger. 2 separate sensors were utilized in this scenario to detect wrist bending. The developed smart device worked perfectly on static gestures and produced good results in alphabet recognition with an overall accuracy of 90%. A Vietnamese sign language recognition system was developed using 6 accelerometer sensors. 19. This prototype was designed for 23 local Vietnamese gestures, including 2 extra postures of space and punctuation. Gesture classification was performed using fuzzy logic-based algorithms. This device, named Axial Glove, succeeded in producing 92% overall accuracy in Vietnamese sign language recognition. A posture recognition system was developed in Ref. 20. This innovative glove-based system was assembled using a flex sensor, force sensor, and an MPU 6050 accelerometer sensor. 5 flex and 5 force sensors were attached to each finger, and an accelerometer was attached to the wrist. The experimental setup comprised data from flex sensors, force sensors, gyro sensors, accelerometer sensors, and IMU sensor data. All these sensors related to Arduino Mega for data acquisition. Based on data classification, the output was displayed on LCD. This system achieved 96% accuracy on average. A real-time sign-to-speech translator was developed to convert static signs into speech by using Sign Language Trainer and Voice Converter software 21. Data were acquired using 5 flex sensors and a 3-axis accelerometer sensor connected with an Arduino-based microcontroller. A handmade sign recognition system was developed with the help of LabVIEW software using the Arduino board. The user interacted with the environment using the LabVIEW provided graphical user interface (GUI), and recognition was performed with the help of Arduino 22. Another smart sensor embedded glove was developed by 23. A good combination of flex sensors, contact sensors, and a 3-axis ADXL335 accelerometer was used for recognition purposes. Flex sensors were attached to each finger of the hand, and contact sensors were placed in between 2 consecutive fingers. The sign language-based gestures were obtained using a described smart glove. These sign-based analog data were transferred towards the Arduino Mega environment for recognition purposes. Classified sign gestures were displayed with the help of a 16:2 liquid crystal display (LCD) and were converted into speech with the help of a speaker. A smart glove based on 5 flex sensors and an accelerometer was designed for sign language recognition. 24. This data glove transferred analog signal data to the microcontroller for recognition. Lastly, the output was shown with the help of pre-recorded voice matched with a recognized sign. A sign language recognition system based on numeric data was developed in Ref. 25. The authors used a combination of a Hall sensor and a 3-axis accelerometer. The smart data glove was composed of 4 Hall sensors attached to the fingers only. Hand orientation was measured with the help of an accelerometer, and finger bend was detected by using Hall sensors. These analog sensor data were passed towards MATLAB code to ideally recognize signs made by smart gloves. This experimental setup was only tested on numbers ranging from 0 to 9. The developed system succeeded in producing an accuracy of 96% in digit recognition. Despite traditional sensor-based bright data gloves, another advanced approach was utilized by 26. A smart glove for gesture recognition was created by using LTE 4602 modeled light-emitting diodes, LEDs, photodiodes, and polymeric fibers. This combination was used only to detect finger bending. Hand motion was also captured using a 3-axis accelerometer and gyroscope. This portable smart glove succeeded in hand gesture recognition made for sign language translation. The authors also made regional sign language systems from different origins. An Urdu sign language-based system was developed in Ref. 27. The smart data glove was composed of 5 flex sensors attached to each finger, and a 3-axis accelerometer was placed at the palm. To display the output, a liquid crystal display, LCD, of 16:2 dimensions was used. The author succeeded in creating a dataset of 300:8 dimensions, and the principal component analysis, PCA, technique was utilized using the MATLAB software to detect static sign gestures. Using PCA, the author succeeded in achieving 90% accuracy. Another regional sign language recognition system was presented in Ref. 28. The authors made a prototype to convert Malaysian Sign Language. A smart data glove made of tilt sensors and a 3-axis accelerometer was developed for recognition purposes. Microcontroller and Bluetooth modes were also involved in this prototype to classify detected signs and transmit them to a smartphone. The microcontroller operated on template matching phenomena and succeeded in recognizing a few Malaysian Sign Language gestures. Overall system accuracy was from 78.33% to 95%. Flex sensor and accelerometer-based smart gloves can perform alphanumeric data classification. Using this prototype, 26 alphabets and 10 digits can be recognized using a template matching algorithm. 29. 5 flex sensors attached to each finger produced an analog signal of a performed gesture which was transferred towards an Arduino Uno microcontroller. Including an accelerometer for hand motion detection, the authors obtained 8 value data for a sign gesture. In Ref. 30. The authors developed 2 gloves-based models. These models contain 10 flex sensors attached to each finger of both hands and a 9 degree of freedom (DoF) accelerometer for motion detection. 2 glove-based systems were tested on phonetic letters, including A, B, C, CH, and ZH. With the help of a matching algorithm, the authors performed static sign recognition with approximately 88% accuracy. American Sign Language Classification Recognition System-based probabilistic segmentation were presented in Ref. 31. This system was divided into 2 main modules. The first module performed segmentation based on the Bayesian network, BN. Data obtained during this session were used for training purposes. The second module was based on classification using a combination of support vector machine, SVM, classifier with multilayer conditional random field, CRF. This system succeeded in producing 89% accuracy on average. The authors in Ref. 32. Brought some innovation in existing sign language recognition systems by combining data obtained from sensor gloves and the data obtained using hand tracking systems. A very well-known methodology known as Dumpster-Schafer theory was implemented on the obtained and fused data for evidence assembling. This fused system achieved 96.2% recognition accuracy on 102-handed ARSL. Hand motion and tilt sensor-based sign data were collected using Cyber Glove. 33. The classification of 27 hand shapes based on signing exact English, C, was performed using Fisher's linear discriminate embedded with a linear decision tree. Vector quantization principal component analysis, VQPCA, was used as a classification tool for sign language recognition. This system was successful in obtaining 96.1% overall accuracy. An Arabic sign language recognition-based deep learning framework focusing on the Singer independent isolated model was discussed in Ref. 34. The main focus of this research was on the regional sign gestures. In a vast variety of regional domains, these authors focused on only Arabic sign gestures and implemented deep learning-based approaches to achieve the desired results. Implementation of hand gestures recognition for posture classification was implemented in Ref. 35. The prototype was purely based on real-time hand gesture recognition. For implementation, an IMU-based data glove embedded with different sensors was used to achieve the desired results. Another advancement in the field of sensor-based gestures recognition was implemented by Ref. 36. A dual leap motion controller, LMC, based prototype was designed to capture and identify data. Gaussian mixture model and linear discriminate-based approaches were implemented to achieve results. A case study-related implementation based on regional data was implemented in Ref. 37. The authors focused on Pakistani sign language models to work on multiple kernel learning-based approaches. Working with signal-based sensor values for classification of real-time gestures was implemented in Ref. 38. The authors worked on wristworm-based real-time hand and surface postures. EMGs and IMU-based sensors were embedded to achieve the desired values of sign postures. An armband EMG sensor-based approach was implemented by the authors in Ref. 39. The main focus was to classify finger language by utilizing ensemble-based artificial neural network learning. The sensor values helped ANN to classify gestures accurately. A sign language interpretation-based smart glove was designed by the authors in Ref. 40. A sensor-fused data glove was used to recognize and classify SL postures. Another novel approach to capture sign gestures was discussed in Ref. 41. The developers of the smart data glove named it SkinGest as it completely grips skin with no detachments. For capturing gestures and postures data, filmy stretchable strain sensors were used. Leap motion-based identification of sign gestures was implemented with the help of a modified LSTM model in Ref. 42. Continuous sign gestures was perfectly classified using an LSTM model to get the desired results. Another novel approach of working with keyframe sampling was implemented.
When here, perfectly classified. Be suspicious.
Implemented in Ref. 43. The authors also focused on skeletal features to utilize an attention-based sign language recognition network. A Turkish sign language dataset was processed using baseline methods in Ref. 44. Large-scale multimodal data were classified based on regional postures to achieve good recognition results. Similarly, the authors used multimodal spatiotemporal networks to classify sign language postures in Ref. 45. Development of a low-cost model for translating sign gestures was targeted in Ref. 46. The main focus was the development of a smart wearable device with a very reasonable price. 2. Vision-based models. The authors in Ref. 47. Developed a model using vision sensor-based techniques to extract temporal and spatial features from video sequences. The CNN algorithm was applied on removed lines to identify the recognized activity. An American Sign Language dataset was used for feature extraction and activity recognition. An Intel Real Sense camera was used to translate American Sign Language (ASL) gestures into text. The proposed system included an Intel Real camera-based setup and applied SVM and neural network (NN) algorithms to recognize sign language. 48. Due to the large
What's this? Real camera. Intel Real. What's Real Sense? What is this camera? Right, is it the depth for depth tracking? Yep, that's pretty steep. An interesting connector. Yeah, so in this competition we are doing a regular camera was used, so there's a Z coordinates in the data, but they not actually used. I guess because the camera is not a depth camera, so it's been told to ignore the Z coordinates.
An American Sign Language dataset was used for feature extraction and activity recognition. An Intel Real Sense camera was used to translate American Sign Language (ASL) gestures into text. The proposed system included an Intel Real camera-based setup and applied SVM and neural network (NN) algorithms to recognize sign language. 48. Due to the large set of classes, interclass complexity was increased to a large extent. This issue was resolved using the convolutional neural network CNN-based approach. Depth images were captured using a high-definition Kinect camera. Obtained images were processed using CNN to obtain alphabets. 49. Real-time sign language was interpreted using CNN to perform real-time sign detection. This approach does not include outdated datasets or predefined image datasets. The authors manually implemented a real-time data analysis mechanism rather than the traditional approach of using predefined datasets in Ref. 50.
What was that?
The authors manually implemented a real-time data analysis mechanism rather than the traditional approach of using predefined datasets in Ref. The authors manually implemented a real-time data analysis mechanism rather than the traditional approach of using predefined datasets in Ref. 50. In vision sensor-based recognition, 20.
Is that a code name for we did the yeah, the word manual in the manually implemented. When a human manually implements something, well, why? Yeah, real-time data. Not yeah. So they it's rather than traditional approach by using predefined data sets in this reference. This paper is from 2009. That's referenced. This paper references a paper from 2009, so it can't be older than 2009. Just open that link somewhere.
In vision sensor-based recognition, 20 alphabets with numbers were recognized using neural network-based Hoff transform, 51. Due to the image's dataset, a specific threshold value of 0.25 was used for efficiency achievement in the canny edge detector. This system succeeded in achieving 92.3% accuracy. 50 samples of alphabets and numbers were recognized by the Indian Sign Language System using a vision sensor-based technique, 52. A support vector machine, SVM, based classifier with B-spline approximation was used, which achieved 91% accuracy on average. A hybrid pulse-coupled neural network, PCNN, embedded with a non-deterministic finite automaton, NFA, algorithm was used collectively to identify image-based gesture data, 53. This prototype achieved 96% accuracy based on the best match phenomena. Principal component analysis, PCA, along with local binary patterns, LBP, extracted hidden Markov model, HMM, features with 99.97% accuracy in ref. 54, in ref. 55, hand segmentation based on skin color detection was used. For hands identification and tracking, a skin blob tracking system was used. This system achieved 97% accuracy on 30 recognition words. In ref. 56, Arabic sign language recognition was performed using various transformation techniques like log-Gabor, Fourier, and Hartley transform. Hartley transform and support vector machine, SVM, and k-nearest neighbor, KNN, classifiers helped produce 98% accuracy. Combined language recognition was performed using various transformation techniques like log-Gabor, Fourier, and Hartley transform. Hartley transform and support vector machine, SVM, and k-nearest neighbor, KNN, classifiers helped produce 98% accuracy. Combined orientation histogram and statistical, COHST, features along with wavelet feature techniques were used in ref. 57. These techniques succeeded in recognizing static signs made for numbers from 0 to 9 in ASL.
So what are the features that succeeded in recognizing the signs?
The neural network produced efficient results based on the feature values of COHST, wavelet, and histogram with 98.17% accuracy. The feature values of COHST, wavelet, and histogram with 98.17% accuracy.
Yeah, I need more details on that. So what's the data is to the images, so doing image processing. Whereas, yeah, in our competition, we're not doing image processing, we're doing the coordinates for each finger, as shown before. And by the way, side note, yeah, turn my thing off, the camera live processing. And yeah, so the current training is only using a 20% CPU. And I don't know, is it because I limited it or not? In terms of CPU, threads, it's using 233 threads. Yeah, it seemed to be using all of them still. So that code we tried in the beginning that meant to limit the training to 4 CPUs only didn't actually work. I think.
The neural network produced efficient results based on the feature values of COHST, wavelet, and histogram with 98.17% accuracy. Static gesture recognition based on alphabets was performed using neural network-based wavelet transform. This system achieved 94.06% accuracy in recognizing Persian Sign Language, 58. Manual signs were detected using the finger, palm, and place of articulation. Equipment arranged for manual sign extracted data from a video sequence and matched it with a 2D image of standard American Sign Language alphabets. The proposed setup resulted in accurate sign detection of alphabets, 59. Deep learning-based SLR models are also focused on vision-based approaches. The authors in Ref. 60 focused on current deep learning-based techniques, trends, and issues in deep models for SL generation. Keeping in mind standard American Sign Language models, the authors in Ref. 61 focused on the development of a deep image-based user-independent approach. Their main work was based on PCA-net features based on depth analysis. Another edge computing-based thermal image detection system was presented by the authors in Ref. 62 they worked on digit-based sign recognition model using deep learning approaches. Different computer vision-based techniques were applied for SLR tasks. A camera sensor-based prototype was used by the authors in Ref. 63. To correctly identify sign postures. A convolutional neural network-based approach was implemented by using video sequences in Ref. 64. A three-dimensional attention-based model was designed for a very large vocabulary to acquire data from video sequences and classify them using a 3D CNN model. Similarly, the same authors implemented a boundary adaptive encoder using an attention-based method on a regional Chinese language dataset in Ref. 65. A novel keyframe-centered clip-based approach was implemented on the same Chinese sign language-based dataset in Ref. 66. The regional Chinese sign dataset was classified using video sequences in the form of images. This vision-based novel approach produced challenging results in CSL. Another fingerspell-based smart model was developed by the authors in Ref. 67. They focused on the development of an Indian quiz portfolio that was based on camera-oriented posture classification. The main point of identification was based on ASLR models using a vision-based approach. A vision sensor-based three-dimensional approach was implemented by the authors in Ref. 68. Three-dimensional sign language representation was classified with the help of spatial three-dimensional relational geometric features. These 3D data were classified and recognized with the help of AS3DRGF-based technique quite efficiently. Another vision-based technique focusing on color mapping-based classification and recognition was developed by the authors in Ref.
This intellectual paper, they use a lot of biased language quite efficiently. How efficiently?
Another vision-based technique focusing on color mapping-based classification and recognition was developed by the authors in Ref. 69. A CNN-based deep learning model was trained on the three-dimensional data of signs. Color texture coded-based joint angular displacement maps were classified efficiently with the help of a 3D deep CNN model. Another advanced approach based on three-dimensional data manipulation for sign gestures was implemented in Ref. 70. The authors focused on classification and recognition of angular velocity maps with the help of the deep ResNet model. Connived feature ResNet was deployed specifically to classify and recognize 3D sign data. Another video sequences-based novel approach to classify sign gestures was implemented in Ref. 71. A BiLSTM-based three-dimensional residual neural network was used to capture video sequences and identify the posture data. A novel deep learning-based hand gesture recognition approach was implemented by the authors in Ref. 72. Image-based fine postures were captured and perfectly recognized using deep learning-based architecture. A virtual sign channel for visual communication was developed in Ref. 73. The author's main focus was to create a virtual communication channel for deaf, mute, and hearing individuals. Another three-dimensional data representation for Indian Sign Language was developed in Ref. 74. The authors used an adaptive kernel-based motionlets matching technique to classify gesture data. A video sequence and text embedding-based continuous sign language model was implemented in Ref. 75. Joint latent spaces-based data were processed using cross-model alignment of a continuous sign language recognition model.
Anyway, it seems like a very biased piece of text. Let's see how many times they use the word perfect. Well, 4. That's probably 4 too many. So I might just find something else and we'll keep going from there. So see you next time. Bye.